So the last topic in chapter 4, work with measurement, is what's called accuracy, precision, and error. I'm mainly going to just kind of mention a little bit with accuracy and precision, but our main topic here really is significant digits. And um, you'll have a better grasp of this if you actually get into jobs like manufacturing and get involved in working with what you can get away with and what you can't get away with to make things work. Some things have to be very precise, some things have to be accurate, and some things have to be both. So it just depends on the situation. A way to describe accuracy and precision is, using like a target. If you shoot a target and you're aiming for the bullseye and you hit everywhere but the bullseye, you would say that's not very accurate. If it's scattered all over the place, we also would say that's poor precision. So nothing can be gained out of this. You just need more work altogether. We can't begin to work with you until something changes. Well, if all of a sudden you keep hitting the same spot on the target, but you're not hitting the actual bullseye, we describe this as poor accuracy but good precision. Now we can work with you. If you ever shot with archery, there's a lot of times what we call sights. Sightings, you can now adjust your sights to work yourself towards what's called the bullseye or accuracy. So now if we hit the bullseye and everything's in the bullseye, we have good accuracy and good precision. So if you ever follow shells, if I can do something one time out of 10, I'm not going to rely on that a whole lot. But if I can do something 9 out of 10, 10 out of 10, we're gonna put some faith and trust in you. So a lot of times that goes with sports and other things. Good precision and good accuracy is what we're targeting. But if you don't have good precision to start with, then we can't work towards accuracy. But this is the ultimate goal: is good accuracy and good precision. So if I'm manufacturing parts, once I get the precision going on, I can tweak things, become more accurate as we go along. But if I'm out here, then we have no place to go as far as adjustments go. So when it comes to precision, what we use are what we call significant digits. But significant digits, is something that gets a little tricky on how to define that there. Hold on a second. So this is saying 1 degree of precision of a measurement is the number of significant digits. So we look at the numbers 2500, there's 4 numbers present. 250, there's 3 numbers present. 25, there's 2 numbers present. 2.5, there's 2 numbers present. 0.25, there's 3 digits present. 0.025, there's 4 digits present. But the catch is they all have 2 significant digits. So the catch is, how do we know what numbers are important and what numbers are not important? So when numbers contains no zeros, all the digits are significant. So that's how the 25, the 2.5, those are clearly significant because there's no zeros. However, zeros are special digits. Sometimes the zeros are significant and sometimes they are not significant. So what we have to do is determine when to keep the zeros important and when the zeros are not important. So the way it works is, if we work with whole numbers, what we do is we start with the leftmost non-zero number, which is usually going to be the far left. What we do is we count each digit, including zeros, until we get to the rightmost non-zero. So that's how, if we start with the 2 and we move to the right, the rest of the numbers are zeros. So those zeros are not counted. We would call that 1 significant digit. 28, since there's no zeros involved, has 2 significant digits. Notice how, again, I start to my left and I keep working till I get to the last non-zero number, which is the 2. So the 1, the 3, and 2 becomes significant, and therefore we have 3 significant digits. If I look at the 2005, I have to count the far left number, and then I got to count everything in between until I get to the far right number that's not a 0, which is the 5. So all of these become significant. We can't throw in those digits out. So this is going to be considered 4 significant digits. So right here, my accuracy would be like to the hundreds place. Here, my accuracy would be down to the ones place. Here, my accuracy would be down to the tens place. Here, my accuracy would be all the way down to the ones place. So I have to be precise down to those place values. So all those come into play. So start with, if I want to talk about decimals or mixed decimals. So this is where it gets trickier, is with decimals. So again, you start the leftmost non-zero number, which again gets trickier because if you look at 007, the leftmost non-zero is actually the 7, okay? With the whole number, the far left number will always be non-zero. But with decimals, the far left actually has zeros in it. So once we get to the far left number, we count to the right, including zeros, until we get to the last digit, including zeros. So here we start with the first number far left that's not zero, which is the 7, and then we go to the right. So since there's nothing else to the right of the 7, that's going to be one significant digit. So we have to be down to what's called the 10th place of accuracy or precision. 2.0, notice how my far left number is the 2's place, the 1's place. If I go to the right, I have to actually include this 0 because I have to actually go down to the 10th place in precision. So I have to be accurate down to the, or precise down to 2 significant digits or to the 10th place. So the 10th place becomes important to me here since it's to the right. So again, if I'm doing decimals, I'll go to the far left, which is the 1, and then you count everything to the right. So it's going to be 3 significant digits. So again, on this one here, again, the first far left number you come across is the 1, and you got to count everything to the right of the 1. 1, 2, 3, 4 significant digits. So that 0 on the very, very end, you have to count it as well. So if I look at this 12,000 plus 1,005, notice that the 12,000 would have 2 significant digits. The 1,005, I would have to include all of it. That would have 4 significant. So if I add these together, that would be like 13,005. But as far as if I really am trying to be accurate, I can be no more accurate than the least significant of the significant digits. So since this is going down to 2 significant digits, my answer can't be any better than 2 significant digits. So we're better off just calling that 13,000 because 13,005 is not going to make that big of a deal in our problem. So 13,000 would become our answer if I was adding numbers and I was talking about significant digits. We're only as precise as the fewest number of significant digits as possible. So if we look at these numbers here, 5,205, notice that would have 4 significant digits. The 12,000, notice how that would only be 2 significant digits. That's whole number math. Now with decimals, the far left number is 3, and then we go to the right. So that would only be 1 significant digit. So the far left number is the 1, and we go to the right, that would be 3 significant digits. 3.02, again, it's a decimal number. So we go to the far left, and then we count everything to the right, and that would be 3 significant digits. So that's how that kind of works. So we have to kind of pay attention to the place values of things. It kind of plays it out there. There's more to it than that, but as we move, if you move more into science and in manufacturing and things like that, it becomes more relevant when you start actually doing the work that goes with that. All right, so that concludes our chapter 4 on measurement.